good afternoon and welcome to the VLSI System Design Lab course. In last term we have already learned how to use LT Spice. We got familiar with LT Spice. Also we have done the NMOS characterization. We have done ID versus VGS characteristics. Also we have done ID versus VDS characteristics of NMOS, and we have plotted a series of plots. ID versus VGS we have plotted for different values of VDS, constant values of VDS, and also ID versus VGS we have plotted for different ID versus VGS we plotted for different values of constant values of VDS, and similarly we plotted ID versus VDS with constant values of VGS. So here I want to go further one step, that if you have plotted series of plot that you have learned, after that you have to calculate threshold voltage. So threshold voltage also you have to calculate channel length modulation parameter. So instead of so many plots, we are requiring only one plot, ID versus VG plot. You can plot. We are using 50 nanometer technology and it is working at 1 volt. VDD is 1 volt. So we will keep VDD equal to 1 volt and we will vary VGS from 0 to 1 volt, and we will plot ID versus VGS, and one set of plot will be there. In that the thumb rule is that under root ID, first I will get directly ID versus VGS, but we also want under root ID versus VGS. So in this graph we are able to see that under root ID is plotted along y-axis and VGS is plotted along the x-axis. So if we plot under root ID versus VGS and draw a tangent on this straight portion, because this straight portion basically belongs to the saturation region, basically because it is following the, here it is it looks like in this region just generally ID equation is following beta times VGS minus VT whole square. Therefore after you have taken under root, then it is looking like linear portion, but in the ID versus VGS plot it will not look like linear, but we have taken under root ID, then it looks linear. And then we are taking a tangent, then it is extrapolated, and wherever it is touching to x-axis, that point we are considering as threshold voltage. So from x-axis we are having some idea that this is the value of voltage on this axis. So this is the thumb rule that we can apply, but obviously directly also we can observe if ID versus VGS plot is there, and wherever its current starts increasing fast, means a significant current we can get, that is called threshold voltage. But if you have to exactly calculate, then you can follow this rule. And also below threshold, this is the dotted line which is showing, you are drawing this dotted line on x-axis, wherever it is touching, this is threshold voltage, but below that also some small current is there. So that small current is called sub-threshold current. Sub-threshold region, below that it is called sub-threshold region or weak inversion region. When VGS is positive but less than threshold voltage, still some, in short channel devices, still some weak inversion is possible. In long channel devices we have discussed that there is no any inversion and it is cut off. In long channel devices, during the derivation we have assumed that there is no any current and it is in cut off region, and no inversion is there. But if you are shrinking the channel length, means channel length is reduced. In the short channel devices, this is not valid. Actually, before the strong inversion, before you are reaching to VT, which is creating a strong inversion. Strong inversion means, what is the meaning of strong inversion? Strong inversion means the channel is created and the number of electron density or electron density in the channel is exactly same as hole density in the substrate. Initial substrate you have taken, and it has some because it is p-type substrate, it has some hole density. It has some p-type charge carriers, so holes. So hole density means whatever bulk channel is not created in whole silicon material, silicon substrate. Only the some portion is inverted. Only some few means up to some depth it is inverted. So up to some depth where it is inverted, wherever channel is there, in that region electron density should be exactly same as that in the bulk material. Bulk material means substrate side, bottom side. Whatever number of holes density, it should be matching with that. Electron density should be exactly same as that hole density in the bulk region. Then we say that material is inverted. In that region, the p-type material is converted to n-type completely. But it is also possible that instead of the exactly same same electron density as hole density in the bulk region, inside channel, maybe electron density may be less. Below threshold voltage, maybe some electrons are present but not up to that level. So if you are below threshold voltage but it is positive voltage, more than 0 voltage you are applying. So you are applying more than 0 means positive gate voltage, but it is less than threshold voltage. In that case, in short channel devices, still some electrons are reaching below the oxide. So below the oxide, still less number of electrons are reaching. Their density is not exactly same as that in the channel. Sorry, as that in the bulk of the semiconductor. So as in the bulk of the substrate, it is hole density. It is not equal to that much, but it is there. Some means a smaller number is there. So it means whatever inversion it is happening, that is called weak inversion. So in the sub threshold region, it is assumed that for the short channel devices, channel is still present. Even the VGS is less than VT but positive. So channel is weakly inverted instead of strong inversion, but weak inversion can be achieved at the smaller VGS. So at smaller gate to source voltages, still some leakage current we are considering. Some current is there, but it is very small in comparison to these currents. So it is very small, and this is small current which is flowing below the threshold voltage. It is called sub threshold current, and this region of operation below threshold voltage and above 0. Above VGS 0, but below VGS is greater than 0, but it is less than VTH. In that region, whatever current you are getting, that is called sub-threshold current, and this region of operation is called sub-threshold region. So in sub-threshold region, some current will be observed, and that in the theory we have seen, and in second, those who have attended in the morning, they have seen, and in the second slot, A2 slot also, I will discuss today. So this is the main reason that leakage current is coming, because electrons are less number of electrons are present, but they are there. Weak inversion is happening. So weak inversion is happening. Still some current is there below threshold voltage, but above threshold voltage it is large current, and the threshold voltage can be calculated in this manner, that we can take under root ID versus VGS plot, and then whatever state portion is coming, it is under root ID. This is why it looks like a state. And here we draw a tangent. If you plot ID, then it will not be linear. If you plot ID versus VGS, it will be quadratic. If you plot under root ID versus VGS, generally it is following quadratic nature, means VGS minus VT whole square. So it is following some quadratic nature, but under root ID is just varying linearly. Under root ID is varying linearly with VGS, and in that case we can draw a tangent here. And we can draw a tangent here, then extrapolate it, and wherever it is touching the x-axis. Touching the x-axis means current is 0. Initially, in all the region there is a current, and after extrapolating here, it is touching, means not exactly 0, but leakage. It is just only leakage current is there. So this point we can treat as threshold voltage. And in the long, even if it is very long channel device, then almost 0 current will be there, but in short channel devices, some threshold current, sub threshold current will be there, so small current will be there, leakage current. So these are these are techniques to find out under root ID versus VGS, and then draw a tangent and extrapolate it, and wherever it is touching, that is threshold voltage. But in the crude sense also, we can estimate from ID versus VGS also. If it is ID versus VGS, wherever current starts increasing fast, that point we can just approximate. From ID versus VDS plot, we can calculate the channel length modulation parameter. If you choose two values of current, suppose one set of plot you are choosing, in this VGS is constant and VDS is varying. So at this point some current is there, that is called IDS. At the second point there is some current that is called IDS. First current is IDS1 and second current is IDS2. So corresponding to first current, which is IDS1, there will be voltage, drain to source voltage, that is VDS1, and for second one VDS2 is the voltage. For IDS2, VDS2 is the drain to source voltage. So by taking ratio IDS1 divided by IDS2, it is just equal to 1 plus lambda VDS1 divided by 1 plus lambda VDS2. That we have seen in the manual in the last one also we discussed that. So why it is happening? Because in the saturation region the equation is ID set equal to beta times VGS minus VT whole square, which is multiplied by 1 plus lambda VDS. So beta times Vg minus Vt whole square, that term is coming in both the equations IDS1 and IDS2. Only the difference is that 1 plus lambda VDS1 is coming in the first current, and the second current 1 plus lambda VDS2. So this is why all the common terms are cancelled out. Only 1 plus lambda VDS1 divided by 1 plus lambda VDS2 will be taken. So in this way, this equation can be means by noting down two currents ID1 and ID2 and corresponding VD1 and VD2, and then taking ratio ID1 divided by ID2 is 1 plus lambda VDS1 by VDS2, and then we can find out. So these are this plot I have, this presentation I have shared to understand this. Now I can stop sharing this one, and I can come to the LT spice so that we can understand how it means whatever I was theoretically telling, we can do it in LT spice. So I will share the screen first. So first let me share the screen, then we can go to LT spice. Desktop is visible. Dear friends, desktop is visible. Somebody
Yes,
reply.
Yes, sir.
Okay. Now I am going to LT spice 17 version. So I think two sets have been opened. I close one. So it is open, and then we have to see. I have already created. I can take that advantage, or I can demonstrate again. So let me demonstrate. It is better that if you have some doubt, that will be clear. So let me create new schematic. Then everything component, diode, inductor, and the capacitor, the resistor, label net, all ground, these are visible. Then I want to make this file for the calculation of VT threshold voltage. So save as, I am telling save as, and then giving the name, suppose VT 2, because first time in morning lab I have made VT1 file. So now VT2 file I will make so that it will be having different name. Then for VT finding I have to plot ID versus VGS. So ID versus VGS we want to plot for NMOS. So take NMOS 4. I am taking NMOS 4 every time. You can, for this experiment, even NMOS 3, normal NMOS also can be taken, but okay, one placement. After that escape, press escape, because only one device I need. After that, what I need? After that, I need some voltage source. Here either we can type voltage that it will go, or we can go to here right side. Then there is voltage source. You can take it. Okay. Then this side one voltage source, connect this side other voltage source, and then press escape. Only two sources you need. After that you need ground. So you can connect ground here. You can connect ground here. One ground you can connect here. You can connect later on through wire. Escape. Press escape. All the three grounds done. Now you need wiring. Take wire here. Then between this one and this ground you can take connection. Then between this source and then gate you can make a connection. Then between this drain here between this drain and this source, second source, voltage source, which is connected to drain, make a connection. Then between this body and come down. So between body and this source, so body is connected to source. Then press escape. All the wiring is done. Then press escape. and after that it is disturbed, so zoom fit. After that you can make the size smaller by clicking here, so make a small size so that space will be there. By default this voltage you can give so what you want, id versus vds. So id versus vgs, so let me cancel it. id versus vgs we want, but you want to give the 1 volt at this source, so you want to give 1 volt. vd is fixed 1 volt because this technology working at 1 volt, so you want to give that much. And also you want to make this source as a vds because it is connected to the drain side, so vds name you want to give. This source you want to give the name, right clicking, give the name vgs. So vgs you have given the name, and this one voltage is not decided, so voltage by default I am giving here 0 because we will give dc simulation command, so in that we can vary whatever voltage we want to vary. So now connection it looks okay. Now next part you have to do what? Next part you have to do spice directives. So edit, then spice directives. Click here. Now we want to use 50 nanometer technology for MOSFET. So 50 nanometer MOSFET model we want to use. So dot include file name is Cmos edu underscore models edu underscore models dot txt. So this is the dot include command will include this model cmos edu underscore models dot txt file. In text file the model is there, so that we have already seen in last one. So okay, and then place here somewhere. After that again one edit command we will give, in which spice analysis, what analysis you want. So DC analysis you want, you can choose there. So spice analysis command you have to give here. By default transient is selected, but after that ECE is there, but we want here DC voltage is only present. So DC voltage you want to sweep, you want to ramp DC. So you want to find out ID versus VGS. So first source you have to take VGS, and only one source you have to ramp. VDS already 1 volt fixed, so this one can be swept linearly between 0 and 1. With increment I am giving here 0.1, suppose 0.1. okay, so place it here also, then press fit, then minimize. So this is, I think all the required things have been done. Then save and simulate. Okay, what is telling? Okay, not simulating. Here we have to provide the name nmos. Yeah, there is some issue because I have done all the things, but still MOSFET name I have not changed. So you can change the name because in model file n underscore 50 nanometer, n underscore 50 n. This is the name, and its length should be specified. You are specifying 50 nanometer because 50 nanometer technology can be having minimum length, minimum feature size is 50 nanometer. Then width may be 0.5 micrometer. Micrometer is denoted by U, nanometer by M, milli by M. So 0.5 micro, 0.5 U. Okay, so now it will be recognized because in model file cmos edu underscore models dot text, the name I have already shown last time, that name of the NMOS transistor, which is 50 nanometer technology transistor, that is given the name n underscore 50n. So this is why that is required here. After that we can run. So now it is after running it is coming something, but we have to choose which one we want to plot. Here we can select, this is the plot ID versus VGS. On the y-axis ID means IDS, drain to source current, and this x-axis is gate to source voltage. Gate to source voltage 0 volt, 0.1 volt, 0.2 volt, 0.3 volt, 0.4 volt, and 0.5, 0.6, 0.7, 0.8, 0.9, and 1.0. So We can extend, it means completely see here. You can see it is 50 nanometer channel length transistor. So in which all the effects we can see. Even sub-threshold leakage current is there. Sub-threshold leakage current is there, and in IDVD characteristics we will see channel length modulation is also present. So we can observe here at the very low voltage, very low value, it is almost looking like zero, almost zero up to 2.2. After that, some leakage will be there. So as I was talking, you have increased the gate to source voltage more than zero, but initially almost completely means though it was positive, but no any inversion was there, but some weak inversion. Here you can see some weak inversion is there. So due to that weak inversion, some leakage current is there. Though threshold voltage is coming here somewhere, if you observe under root ID versus VGS plot and take extrapolate it, and you can get somewhere here. But still some current is there. We can see below the threshold voltage, that is called sub threshold current. And though it is directly ID versus VGS, but we can get from this how to get the data, how to get the if you want to plot under root ID, we can export this data. We can export, right click and export file, then export data set as text, export data as text. This is option. Are you able to see? Again I will explain again. This data you want, ID versus VGS data you want to export, so that you can handle in other software also. So file, then go to data, export data as text, choose it, then it is selecting ID of M1, ID of transistor M1, it will be exported. So click OK, it will be exported. As here file name you have given VT2, so file name which is exported for this file name will be here VT2.ra. This is plot in the this viewer, but in text file its name will be VT2.txt. So that we can see, here in the folder in which I am working. I am working in VLSI lab. Then in VLSI lab I can check it. VT2.txt file is there also. So VT2.txt file is there here. We can see. I have given 0.1 variation, so less number of data sets are there. If you give millivolt, some 10 millivolt, then so many number of data set will be there. So at 0 volt, this is the current. At 0.1 volt, this is 1 into 10 power minus 1 means 0.1 volt. So this is the current. Then at 2 volt, 0.2 volt, this is the current. So order you can see. Even at 0 volt, it was not 0, but it was appearing like 0. It was of the order of some nano ampere, 3.6 nano ampere. Then after that, you are increasing 0.1. So all these currents which are here, they are this at 0 volt. Whatever you are getting, VGS equal to 0 volt. We can see that is basically minimum. But after that you are increasing positive voltage, so accordingly few electrons may be coming, means very weak inversion will be there, and until the threshold voltage is achieved, it is channel is not clearly completely formed, or even channel is not having complete inversion. So complete inversion is happening after VT. You are applying VGS equal to VT threshold voltage. So we can see the current different voltages. 0.2 volt, this is the current, and 0.3 volt, this is the current. Then after that, when you are reaching at 0.4 volts, a huge difference. 10 power minus 9 volt, 9 was the order of the current at here, but here at 0.4 volts, a lot of increment. So it is now 10 power minus 5. So significant increase of current we can see. After that 0.5, still a similar current. Then after that near 0.6, it is very high, minus 4. Then it is almost minus 4 of the same order. So we can see this is the variation. So this one we can plot in Virgin file is still not installed in our laptop, but I will give the Virgin file. I will upload. by next turn you will be having this file, this version software, so in which we can plot this ID versus VGS also. VGS versus VGS will be taken as a first column and ID will be taken as second column, then plot. So ID versus VGS we can plot. After that we can create another column which is taking under root. We can do so a lot of mathematical manipulation in that origin software. In that we can do we can calculate under root of this column. Under root of this column, that will be column C, suppose. So we will plot this column and voltage column and column C. So in this way, sorry, voltage column is this one, current is this one. So this column under root of this column B will be taken. Then we will plot column A and column C, which is column C is under root of ID. So then we can draw the tangent and also we can find out, extrapolate it and find out VT by using completely scientific way, without any crude approximation. No any approximation, it means it will be finding out according to the rule. So even that is also just one of the thumb rule, means for hand calculation. For exact calculation, this the threshold voltage equation is very complex, and in the BCM4 model it is very big equation that is calculating according to that. Simulator calculates according to that, but for our experiment we can calculate from this basic rule. So it is the way by which we can find out the this threshold voltage. So this is the ID. When you will take under root ID versus VGS, then it will be some different value, and then we will draw the tangent here in this one in the origin software and extrapolate here. Somewhere it is cutting, somewhere here we will get. So threshold voltage will be decided based on this. Then I can stop, close this graph. Then also we have to do ID versus VDS. Then ID versus VDS plot. From here itself I will do. I will not draw all the things. By changing this VGS as VDS and giving here gate to source voltage, fixed voltage, here we will give 1 volt, and here we will provide by default 0, and we will ramp this VDS. So in the same file, or we can make a new file lambda for lambda also. So lambda file already I have made, I will open. For lambda we have already made, which I can open instead of designing. So I will not take time in designing. A lambda file is already there. So this is the file which is going to calculate, with the help of which we are going to calculate the channel length modulation parameter. So here we can see we have provided fixed gate voltage 1 volt, and here by default 0 we have given for this source, but in here voltage .dc VDS is varying from 0 to 1 volt, and here 10 milli variation is given, but instead of giving 10 milli, better to give 0.1 volt, so that number of data set is number of data set is less, and exactly at 0.1, 0.2, 0.3 the calculation will be done. So here we can see circuit is same, only the variation is done here. The changes is done that VGS is fixed now 1 volt and VDS is varied. This the DC VDS 0 to 1 volt with increment of 0.1 volt. Then we can run it. Hello. This one run. Why two plots are there? VGS one we can close. VGS we don't require. This one only. So again run. We don't want downside. Close it. Again run. We want to see upper side. So after running, it is blank. But if you want to see ID, you choose ID. So this is the ID. This is the ID for given VGS and VDS. VDS is varying from 0 to 1 volt with increment of 0.1 volt, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 up to 0.8 and 9, then 1.0. And accordingly the current which is coming, we can see. So we can see this region. Are you able to see the plots? Dear students, are you able to see the plot IDVD?
Yes, sir.
Good. So at least you should choose the saturation region enough saturated. So here we can see, because it is the short channel device, where 50 nanometer channel length we are using much less than 1 micron. So all the effects are present. Channel length modulation is present. Some threshold leakage is present. We can see here. Suppose you have taken at any two values you can choose around suppose 0.8 volt, what is the current, around 0.9 volt, what is the current, or around zero point 0.8, and then at 1 volt, what is the current. So we can choose two set, one set at lower voltage, and other one at higher. So if first set I am telling IDS1 and corresponding voltage as VDS1, and second set as IDS2 corresponding voltage as VDS2, then IDS1 divided by IDS2, which is giving 1 plus VDS1 by 1 plus VDS2. So by this method we can get the lambda, because IDS1 is known, IDS2 is known, VDS1 is known, VDS2 is known, only lambda is unknown, so that we can solve and find out lambda. So again here if marker is there, then we can directly read. If not, no issue, we can export it. We can export it here, export, then file, then export data, data as text. So okay, already some exportation I have done, because this file was already there. So if you want to keep it, leave it, no problem. Cancel it. Again we can save it with some separate name. We can save it with separate name. Save as lambda 2. Suppose lambda 2. Second time we are doing some. Save. Now run it. Then plot it. Then now we can export. Right click, then file. Inside file there is option export data text. So ID of M1, ID of transistor M1. Okay, we can see now in this same directory in which we are working. So lambda we have, lambda 2.txt. So this one is giving you ID. So we can see at 0, this is the value of current, which is almost, we can say 0. At 1 point, means at 0.1, this is the value of current. At 0.2, this is the value of current. And at 0.2, 0.3, almost similar. Order is similar. Even at 0.4, means near 0.3, it is 2, and after that it is much increment, which is 2.4. After that at 0.5, 2.6, and then order is same, but increment is there, some increment is there, we can see. So what we want, suppose you have chosen some exactly, it is not same value which we have provided. We have provided something 6, then 7, then 7.99. Why it is giving 7.99 means that is 8. This 7.99 is, this is 0.8, and 8.99 it is 0.9 actually, and this is last one is 1.0. So suppose you are taking 7, this one 0.7, and this last one. So for 0.7 this is the current, and for 1.0 this is the current. So this is suppose 0.7, 0.7 is VDS1, and the one you are choosing VDS2. So also you are knowing VDS1 and current IDS1, you are knowing VDS2 and current IDS2. So by plotting, by taking ratio VDS1 divided by VDS2, 10 power minus 4 E, wherever it is writing E means 10 to the power minus 4. In this text file which is generated, E is basically indicating 10 per power, 10 to the power minus minus whatever. So 10 to the power it is indicating. So basically here for the 0.7 we are getting 2.865509 into 10 power minus 4, and here it is 3.1. So basically minus 4 power it is cancelled out, only 2.865509 divided by 3 point means This is yeah, second one is 3.16211 like that. So IDS1 by IDS2 it will be giving like that, and VDS1 VDS2 this 0.7 and then 1.0. So put it in equation and find out the lambda value by solving. So this is possible because exact value of the current you are able to see in the text file. By exporting text file, we are able to see what is here exactly. It is not directly visible, but by exporting this data in text file, we have set up plots. We have means two columns. One column is giving the voltage, other is giving current. So at which voltage, what is the current exactly we are knowing. So accordingly, by choosing two values of current here in this saturation region and taking ratio of them, we are able to find out channel and modulation parameter lambda. So it's fine. Now we can move to PMOS demonstration. So I will stop here, or if you want to make the circuit, you can make it. And basically already you know it. Next I will close it and I will show a PMOS type of device and how to characterize. So I will open PMOS already there. So PMOS IV as here. Here I am not going to draw again. I am showing here. So this is PMOS which is taken from here. Taken from here. This is PMOS, and here what is the means significance of the different nodes. Here it is gate, this one is drain, this one is body, and this one is source. Source is on the top. Source, gate, drain, and body. So this one is taken here. Source, then gate, then drain, and this is body. So body should be connected to the highest potential in the circuit, highest potential point in the circuit. In this circuit, highest potential point is this ground. Ground is 0, but in this sources we will apply negative voltage because it is PMOS. So we will apply negative drain to source voltage or gate to source voltage. All are applied below 0. By default we are giving 0, but we are giving negative, minus, it is increasing by 0.2 negative. So if you want to find out ID versus VDS characteristics, then what you are doing, DC simulation command you are giving .dc VDS, which is increase below 0 you are providing. So 0, then minus 0.1, then minus 0.2, then minus 0.3, then minus 0.4, then up to minus 0.6, minus 0.8, and minus 1.0. But constant VGS also should be there. So VGS will be constant, but it should be means magnitude wise. Magnitude of VGS should be, though it is negative, but its magnitude should be more than the threshold voltage. So threshold voltage somewhere if coming at minus point something, minus 0.3 around, then it should be more than that. So that we can see from this circuit, same circuit we can simulate. And again, basically the name of transistor we have changed P_50, and because it is PMOS, in the model file name of the transistor is P_50 nanometer. And we have also given the name of the source VGS, this source VDS. By default 00 we have given, but we have given the actual value of voltage here. .dc VDS 0 to minus 1 volt with increment of minus 1 volt. VGS 0 to minus 1 volt with increment of minus 2 volt. And also we have included the model file by SPICE directives here, by SPICE directives, and analysis command .dc command we have given from here, that analysis command. So also here also SPICE directive commands we can use. Here some symbol, this is SPICE directive we can open from here, and from here text we can add. I think mirroring can be done. So many other facilities are there. So here is SPICE directive. If you want to open from here, you can go, or here we can go. SPICE directive and SPICE analysis means control file for the SPICE what simulation you want. So that is specified here. By here we have gone and we have given that we have fixed already. One source we have given, any one source I have chosen here. I have not given any because here we want to plot a setup plot, but during the calculation, threshold voltage calculation, no need of all the sets, only one set you can plot. But here we want to demonstrate first set VDS we are varying VDS and want to find out ID for fixed values of VGS. So first setup plot means the source is voltage source is VDS and it is varying from 0 to -1 volt with linear variation with increment of -0.1. Then second source we have specified, that is VGS. It is also linearly incrementing and 0 to -1 volt with increment of 0.2 volt. So these have been given, which is already visible here in this command, in this text file. So all these you have completed and all the model file provided. Then you can simulate it. It is already ready to simulated. So you should not click here. It is not required. Actually, drain is here. So you should click here. So drain current ID is possible from here. So we can see the current is negative. We can see current is coming downside. 0 is here. So coming down, negative current, and voltage negative. So just it is opposite of that. Wherever we are getting for positive side in the NMOS, just it is opposite in opposite quadrant. What in which quadrant? First quadrant you are getting ID versus VDS characteristics of the NMOS. We are getting in first quadrant. It will be in third quadrant. So if you plot together, then you will see this plot will be in first, second, third quadrant. It will be in third quadrant. Yes. So just symmetrical, but in opposite quadrant. And also we have made here means same current we want. So therefore, we want same level of current. So also one more thing we have done, that here we have provided double channel width. We have given double. In NMOS we were taking only 500 nanometer or 500 nanometer or 0.5 micrometer, we can say. Here 1000 nanometer you can give, or you can also give 0.5 U means micron. Channel length is same, but width is, oh sorry, not 0.5. You want to double the channel width, so 1 micron, 1 U you can write. It is PMOS, so you can write 1 U. So 1 micron width is given, and also channel length is same. So by that way we are getting the same current and symmetrical. It is symmetrical, but in opposite quadrant. First quadrant was in this plot was coming in first quadrant. In the case of NMOS, it is coming in third quadrant. Means voltage is negatively increased, VDS is increasing in negative direction. Similarly, current is coming downside, means negative direction. So this is done ID versus VDS characteristics. And from the same graph we can means from the same circuit we can also do ID versus VGS. If you have to do ID versus VGS means transfer characteristics, then we have to modify this one. First source should be VGS. This first source should be VGS, and second source should be VDS. So here I am modifying. Then okay. Then simulating. Then this new setup plot we can get. So we can simulate, and then here we can click here. We are able to see this is the plot. So we can see how it is looking like that. So at VDS 0, very touching, it is almost touching, but VGS is more 0.2, then 0.4, then 0.6, then VDS is first 0, then VDS is 0.2, then VDS is 0.4, 0.6, 0.8, and then 1.0. VDS is here 1.0. So in this way, ID versus VGS plot is there. We can see initially the current is almost 0 here up to some voltage, even up to 0.2 volt, no current. More than 0.2, you are coming very near to 0.3. Then very small sub-threshold current starts, and here somewhere after threshold voltage is achieved, means after 3.3 volt somewhere here threshold voltage you can get. So after that current is increasing very fast. So we can see this is the situation. So again for PMOS, this is ID versus VGS characteristics. Previously we plotted ID versus VDS characteristics. After that, one set of plot you can do for the VG calculation, gate to source voltage calculation, in the similar fashion as previously we have done for NMOS, and one plot for the channel length modulation parameter calculation for PMOS. So for PMOS also we can do all this. Also body effect I have already told that though I have not given any demonstration for that, that you can do. Instead of in N channel or P channel both we have to do. Instead of connecting this body to this one to this any source, either here in the case of PMOS it is connected to the highest potential point. In NMOS it is connected to the lowest potential point, but it is disconnected and connected with some separate voltage source, and we are varying that voltage. Then we can see IV characteristics how it is varying. So that will be a study of body effect. So this is also possible. After this, I am interested to go for CMOS inverter, but before that, I can ask some questions if you have any issue in understanding or any problem not able to sort out, not getting simulation results. So that we can discuss now. After this, I want to explain CMOS inverter VTC plot. VTC plot means voltage transfer characteristics plot. That is output voltage of the CMOS inverter plotted along y-axis and input voltage of the CMOS inverter plotted along the x-axis. Then how it looks, how the VOH, VOL and VIH, VIL, all these calculated, all those, and then how noise margin is calculated, all this is possible. So maybe calculation will be done later on, but today design part we can do. So that I want to do, but before that let us have some any queries, any questions, any doubt, any difficulty you can ask. Do you have any problem or we can move? Dear students, should I move forward?
Yes, sir.
Yes, sir.
Okay. So I will move forward. So all the explanation I am doing, you can even do later on. Recording is also there. So this one I am closing this circuit. PMOS characterization done. This circuit you can note down. This is the circuit required for the IV characterization of the PMOS. The circuit is same, only the DC simulation command you can change. Then ID versus VGS or ID versus VGS we can get accordingly. Model file and all included. So next I want to show the CMOS inverter design. No, I don't want to save changes. Then CMOS inverter design. Open. I have already designed. So design. If I will design, then it will take some time. CMOS inverter design I will take directly, which I have done for VTC plot inverter underscore VTC.asc. So then here we can explain. So as here we can see on the top side, this is PMOS, and this is source. This one is upper side is source of this PMOS, and downside is drain of this PMOS, and this side one is gate, and this is NMOS. Upper side is drain of this PMOS, and lower side is this one is source of this PMOS, and in between this is body. Here also it is body of the PMOS. It is body of NMOS. And then this is gate of NMOS. So gate of both the transistors N and PMOS are connected together, and drain and both the drains are also connected. Drain of PMOS and NMOS both are connected, and from the common point we are taking some output. Here we have made some output port, and from the common point which is gate is connected. Here we are giving the input. So here we are making input port at which we are connecting some source which is by default 0 voltage is given, but also its name we have changed that instead of V1 it is given the name V in, which indicates that input voltage. So here dot DC V in 0 to 1 volt with increment of 1 millivolt. We are giving the command spice simulation command. So it will do DC simulation, and it will provide this voltage V in. This voltage source will be varied from 0 to 1 volt with increment of 1 millivolt. So V in is varying from 0 to 1 volt with increment of 1 millivolt, and also these are the simulation related commands. Also we have provided the model file that includes CMOS edit underscore models.txt, and also we have done some editing parameter name of this transistor. We have, for PMOS we have made P underscore 50, and the channel length we have provided 50 nanometer. channel width we have kept 1 micrometer, which is double of the channel length of NMOS, so that same current can be produced by this transistor also. Here we have also done the same thing. Name of the transistor we have made N underscore 50 nanometer, length is 50 nanometer, channel length, width we have given 0.5 micrometer. So here width is 0.5 micrometer for N channel MOSFET. Here width is, here width is 1 micrometer, double, because mobility of the holes is just half of that of electrons. In N channel MOSFET, whatever electron mobility, it is more, and if compare mu p by mu n, it is coming 1 by 2, or mu n by mu p is 2. Mu n by mu p, mu n is electron mobility, mu p is hole mobility, so mu n by mu p is 2. So it should to compensate same, means to get the same amount of current, we have to keep width equal to 2. So 2 times of that of NMOS. Therefore this is done like that, and we have also provided the highest voltage, means supply voltage is VDD. VDD is 1 volt. VDD is connected to this one source, and it is now also body of the PMOS is connected to the highest supply voltage, because in this circuit we can see for the NMOS we are connecting body of the NMOS to the lowest potential point, and body of the PMOS we are connecting at the highest potential point of the circuit. For this circuit, complete circuit, this is the highest potential point, that is 1 volt, and for this circuit lowest potential point is ground, 0 volt. So this is why this body is connected to the lowest potential point at the ground, 0 volt. For the PMOS, body is connected at the highest potential point, that is potential difference here with respect to ground is 1 volt. So it is highest, means positive we can say, most positive or most highest potential. It is just relative. So relative to others it is highest. So in this way it is ready to simulate, but also we can also tell one more thing. If you press control, then right click on the transistor, then it will be showing this window. Then this channel length also, here in this symbol I am showing channel length also. So by selecting this value L equal to 50 nanometer, W equal to 1 micrometer, then by double clicking here it will be selected. So visibility will be selected, or here also visibility is option is there. By choosing here, then selecting here. Oh, gone. Cancel. First press control, then right click, then it will be coming, and initially it was not visible in the other circuit we have seen. So by choosing here and then selecting is here, then it becomes activate, means visible is selected, then pressing OK, it will be becoming visible. So nothing to do, already it is there, but when you are doing new, then it will not be visible. This L and W will not be visible. To make them visible, we have to press control, then right click, and then they are select visible, means check it. When it is checked, then it will be visible. So this is another extra point, and another point is that we are making here one input port, and that point is here output port. Though it is not required to show the port, how to create port, that is given. If it is not, then no problem, this voltage is already connected. But during the creation of symbol, we will remove this voltage sources, this ground, and this voltage source also. Only we will make an input port, VDD port here, and a digital ground port here, and one input port at input and one output port at output. Then we will create a symbol to further use it, this inverter circuit, to any other higher level of design. So that is why, so input and output ports must be required. Input port, output port, VDD port, supply voltage port, and the ground port. So that is means that will be done also next turn. But here let me explain these two ports, input port and output port is there. So how it is done? Because here there is some label net. Label net option is there. Initially you connect a wire, and without any port or without any this type of input port, output port, it will be there. But if you choose here, then you can give the name. So you can give this name in. and then here select it is input or output, output or bidirectional. So you can choose input because it is you are making input port. For this output port you can choose output. For this BDD you will give the name BDD and then input port you will select. For here digital ground by downside digital ground we will give the name DG and D, and then you will choose the input port. So this is I am cancelling because it is already done, so not required to choose, but it is possible. After that after clicking OK and then put it here, it will become like port like that, and here you put then output port. So these are few things which you can see. After this I can do the simulation because DC simulation commands are already given, and this MOSFET model file, 50 nanometer channel MOSFET model file or 50 nanometer node MOSFET file is MOSFET model file or MOS model file, SPICE model file for the MOSFET is already included. Then we can simulate. This is simulating with the help of BSIM4, Berkeley University, California. They have BSIM group. They are developing they have given the terminology BSIM name. BSIM stands for Berkeley short channel, means Berkeley means Berkeley University short channel IGFET. IGFET means insulated gate field effect transistor, which is also MOSFET. So Berkeley short channel IGFET model. So Berkeley short channel IGFET model, initially its name initially the model was developed, that is called VSIM3. It has also so many developed versions. So VSIM3 at different versions it may be specified. So, and similarly VSIM4 is another model which is further improved, and then further many other VSIM 5, 6, and VSIM CMG, VSIM IMG, VSIM for multi-gate means FinFET based model, VSIM common multi-gate and VSIM CMG common multi-gate, and then IMG VSIM independent multi-gate. So all various models they have developed. So from there means model, that is VSIM4 model we are using. This is also used in all the design houses. In semiconductor industry, people are designing various circuits based on VSIM3 or VSIM4 model, at least this up to this technology node. And if you are going much down, then maybe some modifications are required. So finally we are going to simulate with the help of VSIM4 model. So let me just run. After that, what you want to see, you want to plot output voltage with respect to input voltage. So okay, click here somewhere. Output voltage is coming. So output voltage is initially constant. After that, some negative slope, then coming down. Then here some negative slope. After that, becoming minimum. And also you want to see the input voltage, how it is varying. What happened? Let me simulate again. I have pressed somewhere, so it is gone. So let me simulate again. Then we want what we want. We want this output voltage. Click here. Also we want input voltage. Click here. Then we can see the graph. So this is the complete plot we can see. So basically this line is showing that V out is equal to V in. At this line, if you are at this line, V out output voltage is equal to V in. This is showing, but this is actual one. This is green one is actual one. Initially it is constant, then after that it is coming down. So initially it is initial it is swinging between 1 volt and 0 volt. This much swing is possible here for Cmos inverter, and between BDD and 0 it is swinging, and initially it is constant. The operation will be explained in theory in coming lectures. And here we can see here some negative slope is there. First negative slope, second negative slope. Negative slope is dV out divided by dV in. Differentiation of output voltage with respect to input voltage. So dV out by dV in is here negative slope. dV out by dV in is -1 here. Here also it is -1. So from first point where dV out by dV in is negative, if you draw a perpendicular to y-axis, it will be touching somewhere on y-axis, and that is called VOH, means output high voltage. And similarly, you draw a perpendicular here, then touching to x-axis somewhere, it is called VI, input VIL, input low voltage. It is called input low voltage VIL. Then second point is there where negative slope is there. From there, if you draw perpendicular here, it is called VOL, output low voltage. And here, if you draw perpendicular to x-axis, it is called VIH. It is input high voltage. So with the help of this VOH, VOL, VIL, VIH, we will calculate noise margin, and also we will do the transient characteristics. In transient characteristics, we will instead of providing this, I can close it. Instead of providing this DC voltage, here we will provide some pulse in which some pulse width will be there. It will be high for some time. After that, it is low for some time. Then again high for some time. So basically, pulse will be connected here, and then we will simulate with respect to time. Means output will be plotted with respect to time. Also, input will be plotted with respect to time, and we will see that output is inverting. Pulse is high, then output is low, and pulse is low, then output is high. So this inverter is inverting the pulse. In this one also we can see inverting. When input is low, then output is high. In this one also we can see. You are giving 0, then output is the maximum. Output is at 1. And when you are giving maximum 1, then output is at 0. So like that in VTC plot also visible, but with respect to time it will be more clearly visible for that. And with the help of that we will calculate the time delay and all. So it is means demonstration part. I think demonstration part done. Now I can handle some problems if somebody out of this complete class, if any student is facing any issue, that we can resolve. I am stopping the sharing now. If required, again I will share. So next is to handle means problems. If any student have any problem, you can now tell me, and I will make you presenter. I will make you presenter, and then you can try. You can demonstrate here, and we can resolve. You can share your screen, and we will discuss, give the instruction and try to resolve. If any problem, dear students, out of all students, if any student is facing any issue in designing the circuit with the LTS spice, in doing NMOS characteristics, PMOS characteristics, and in inverter today I have explained, then it will be done, we will do later on. But in last 2 lectures, whatever we have done, you are able to do. Calculation part is different part, but simulation, at least schematic design and simulation, model inclusion, spice command inclusion, and then running the simulation, getting the plots, if it is coming properly. And if you still any doubt today or any coming lectures also, you can tell me. I will try to resolve. Still we have time, and I think this much time which is remaining, that I can give to you for resolving the issue. If you have any issue, we can resolve it. Somebody have any issue? Nobody is responding. If either you have any issue or not issue, if not, then also you can tell. No, okay, no problem. Then that's good. That's great thing. If you are able to do, that's very good. And only calculation part it is remaining. Rest design part and also understanding of the software, that is clear. So that part we can do in coming lectures. Before that, even you can do. If anything still remaining, I can demonstrate later in next lecture. So should I stop recording if anything extra needed to be explained, or should I stop here recording? There is some time you can do the design of inverter, you can do by yourself. If you have some problem, I can explain. Because I demonstrated, you need some time to draw the circuit, to understand, to include model, to include the spice simulation commands, to run it, to understand the VTC plot. At least this much if you have to do, or PMOS study you have to do, so you need time. So every time I am explaining, then you cannot get time to understand and to do yourself. So now this time, remaining time, you can do by yourself, and I can explain if any problem comes. Should I stop recording now? Or anybody wants to share his screen and his or her screen and wants to discuss some issue, some problem, troubleshooting? Nobody has any issue, I think. So if nobody has any issue, then I am stopping the sharing of the screen. Sorry, screen sharing already done. Stop, but I can also stop recording because unnecessarily recording is not required. If any demonstration is there, if somebody is having some troubleshooting issue and we are troubleshooting, that can be recorded, but if not required, we cannot we don't need to record.
Yes, sir.
So no issue?
Yes, sir, no issues.
Okay. Good, very good. So I am stopping the recording. Now still I am here. You are